the benefit that we have is these little beads are basically like magnets instead of sponges, right? And the magnet is the chemical interactions between the amines sitting on the surface of the graphene, which gives it a stable space to sit on, and also they don't have to keep getting regenerated. And then the carbon dioxide molecules are attaching to this particular amine.
Welcome back to Digital Innovations in Oil and Gas. And in today's episode, I am exploring this really fascinating world of direct air carbon capture. The load of CO2 in the atmosphere is now at a level where we do need to invest in tools to extract more carbon than the planet itself can do organically through forests and the like. And on today's episode, I'm interviewing Samir Adams, who is an entrepreneur in this domain. With a really clever innovation that might be a great addition to the arsenal. Samir, welcome to Digital Innovations in Oil and Gas.
Thanks, Jeffrey. Appreciate you making the time to talk about a very important topic to all of us and future generations.
Yes, especially in light of what's going on in California this past winter. It's been a real tragedy, and getting ahead of this issue is really, really important. But first, let's, if you don't mind, just introduce your a little bit of your professional background and how this whole how you got into this whole question of carbon mitigation as a career.
Yeah. So my business partner, Fernando Sanchez, and myself, we're both engineers by trade. We work for large companies across startups. And about 5 years ago, we reconnected at a Panera Bread of all places, right? And just kept on talking. And we were looking around for something exciting, interesting to do. We had several interests we were pursuing at the time. But we looked at what's going on the greenhouse gas side of the house, and we saw there things that were not really making sense to us when it came to efficiency in the market. So we said, hey, let's take a crack at this and see what we can kind of come up with here.
Well, let's. What are some of the things that really came to light? I mean, if you talk to professionals who work in clean tech and decarbonization, they may be missing some things here. What is it that you guys saw that you feel was important enough to devote time and energy to fix?
Yeah. So, and this is something we discovered as we get more into it, right? There's a significant lack of transparency we feel in the field, and there's an incredible amount of expense involved in capturing very minimal amounts of CO2 for the capital cost of building a site out. And if you take a look at the cost per metric ton, it's well above US DOE's $100 per metric ton target. We're talking anywhere from 650, 900. It's really expensive. That didn't make sense to us, right? Having both been business executives as well, we were looking at the store and like, there's got to be a better way, right? And that's when we put our entrepreneurial caps, like, let's figure out what we can do here.
Yeah, and I think the combination of technology background, so your fast iterative cycles, and as well as an engineering background, I think is really a really intriguing combination. What is it that you've worked on or led you to this innovation that you've got?
Yeah. So we talked to a bunch of different academic institutions around the world, a lot of Ivy League schools, and everyone had bits and pieces of the puzzle, but nobody really was able to put it together. We had a concept, we had an idea, we shopped it, talked to a few different industry folks, and we came across an engineering company out of the UK, Haydale, who's a really good engineering partner of ours right now, we're a partnership with. And they had this missing link to us, which was basically they were able to take functionalized graphene and create an ink out of it, out of polymer base. And we came up with this little thing.
It's a little ball. What is now? It's black colored. So what is the? And so what's the graphene angle here?
Yeah. So it's a little ball because you think about from a science engineering side, the maximum amount of surface area you can expose in the sphere. Yep. So we said, all right, let's grab some ceramic balls. They have the polymer ink. We coat the balls with polymer ink. So the thing with the polymer ink, and the reason they're black is because this is basically graphene right now.
So it's a graphene ink.
Yep. So you take all those graphene chips, you pull them into the ink, and that's where you get the graphene ink. Now, the magic here is what happens to the graphene before it gets put in ink. They have Haydale has a plasma functionalization process that they can combine different compounds and molecules and atoms into the graphene itself for different functionality, like strength, for example, durability, that sort of stuff.
Right.
We had a slightly different story that we wanted to see if they could actually pull off.
And then that story was, how do you kind of track CO2 or some other gaseous molecule to the surface of that ceramic ball?
Yeah, exactly so, right? So we'd already looked at all the science, and the science made a lot of sense. There's a lot of lab scale stuff that really
Yeah,
wasn't feasible. So
yeah,
uh, everybody knows amines have different capabilities, for example, right? So I'm not giving anything away here. It's fully patented, covered. But if you take amines, you just throw them on the ground, they're not really going to do very much. So
mm,
we were trying to figure out a way to bind into some sort of surface. We thought about graphene. Our initial concept was a plenum type system. It was really hard to make graphene in those sizes based on the graphene companies we talked with. So really, Hagel's last step here was, hey, they have an ink process. So we took the functionalization of the graphene,
yeah.
plasma functionalization, into the graphene surface of amines in this particular case, but we can do other things like MOFs and COFs or other greenhouse gases as well. So our patent covers it all. And their capabilities, engineering capabilities, covers it all. And we're able to take that, slap it into an ink, put it into this little bead, coat it, dry it, and then these beads have gone 20, 30, 40 cycles regeneration. They're pretty effective in the direct air capture unit that we've created. We're capturing roughly about 10% right now, but that's like a TRL7 level, right? So there's some engineering to be done and tightening it up. The science says we can hit 99%. Commercially, if we hit 85%, we're going to be doing really well. We're going to be significantly under $100 a metric ton.
So if I were to visualize this, we have you pull air from the atmosphere over a collection of these ceramic balls coated with graphene and amine. The carbon dioxide or other whatever molecule you're after clings to the surface of that ball, and is now removed from the atmosphere. But now you have ceramic balls covered with carbon dioxide. How do you disconnect the CO2 from the ceramic, and then what do you do with it after you've collected it?
Yeah, so we scienced the heck out of it, right? So this is the part about the approach that we took. Currently, the concept in the industry today is they have sponge-like materials, right?
Yeah.
They function, they add their compounds, and it could be amines, could be other stuff. Then there's a lot of solvents, high amounts of heat. There's other companies that are doing accelerated geological processes that are having 800-900 degrees worth of heat, right? So the release process is where the vast majority of the energy is being used. The benefit that we have is these little beads are basically like magnets instead of sponges, right? And the magnet is the chemical interactions between the amines sitting on the surface of the graphene, which gives it a stable space to sit on. And also, they don't have to keep getting regenerated. And then the carbon dioxide molecules they're attaching to this particular amines. Now, to release them, a low-level electrical current. And here's the entire genius how this all kind of came together. Graphene's conductive, ceramic is resistive. So the graphene passes electrical current through its surface, which kicks off the CO2 from the amines, but it keeps the amines tightly bound still because they're plasma functionalized onto the graphene surface. Now, the ceramic's resistive, so it heats up a little bit. So now we have an electrical thermal reaction that helps release the CO2 at very low current levels. And that's, at the end of the day, what made the difference in terms of capturing the capture costs, right? Because, like you said, it releases the other part of it. So
so you actually have that low electrical current. It means you are more grid compliant. You can locate this device wherever you've got grid access, as opposed to beside a large power generating facility, or you're having your own gas turbine, which is what a lot of carbon capture energy requirements are. It's large scale utility grade power to be able to do this, and you can do this at a much lower scale. So what do you do with the CO2 once so you pass the electric current, disconnects from the ceramic sphere, now you have CO2, so how pure is it? And what could you do with it? Like, is that the commercialization dimension here?
That's the commercialization dimension, exactly right. So it turns out we don't need to have filtration systems. We don't have to go through any other sort of processes, chemical processes to do this, because it's only CO2 that's binding onto the surface. So you think about this, you create a light vacuum, you pass electrical current through, now you have basically a pure CO2 stream coming off these spheres, and then you just flip the valves back around, the auto regeneration mode, where air comes in. What we do with the CO2 is kind of interesting, right? We never really believed in the whole sequestration part of the story, right? Again, as business folks, we have to make money. We can't depend on government largesse, taxpayer money, transfer of wealth between nations. And that's all fine and good and well to start the process, but you have to be commercially viable long term. So we started doing some market research, and we realized there's an incredible amount of CO2 demand around the world. That was the thing that really surprised us. We effectively have gold in the air that's harmful to the planet and our health that we're burying underground. Meanwhile, we have whole slews of industry here saying we need CO2.
CO2, yeah. And so if you now you have a box that can generate effectively pure grade or industrial grade CO2 at a
Yep.
more localized level, and perhaps even in a volume suitable for a specific industrial application. Where is CO2 commercially interesting? Food
Yeah.
industry, perhaps.
Perhaps.
Yeah. Where else is it
Yeah.
valuable?
Yeah, so everybody thinks about soda, right? And that's actually where a lot of CO2 goes to today. It
Yeah.
has to be food grade, however, right? So it turns out one of the biggest consumers of CO, well, the domain that has the most demand for CO2 is actually oil and gas,
Mm.
enhanced oil recovery. So the idea is you take CO2, pump it underground, it helps push all the oil that's trapped into the rock
Yeah.
out and into production, right?
Yeah.
It has a side benefit of sequestering most of the CO2 that goes in there and regenerate through again. So obviously, as anyone who's been around an oil field has, and I've actually spent more time around them recently, lots of methane, of course, lots of CO2 as well. Now they have to pipe it in from 5,500 miles of CO2 pipeline, right, throughout the Southwest, and cost is expensive and so forth and so on.
Yeah.
Now, if we set up these units, which can be as small as a square meter, but obviously we like to go to a full-size shipping container, they can get the CO2 directly on site, captured, integrated right back into their pipelines. And then from there, you've got cement and steel as well, right? Agriculture is one too. Our game changer is we can capture at the source, put it right back at the source at a much lower price.
Yeah, that's a dramatic improvement. And of course, now you've got the value stream of carbon dioxide creating the commercial dimension because the market will pay
Yep.
for the CO2. And I'm sure there's other useful applications besides those two. Now you mentioned the economics are really compelling. It sounds like, so if you think about it, right, your electrical demand, your energy demand to run the device is actually quite low. You only need a couple of fans to push air around, and then an electrical current to regenerate to remove the CO2 as captured. Is this one of the where you get down to the very, very low operating costs relative to other large scale services?
Yeah, no, exactly. That's exactly it, right? We have three fans in the entirety of the unit, no matter the size of the unit. Bunch of ductwork, stuff that's off the shelves, right? We're not really custom creating anything. So right off the bat, our capital costs are much lower to create this stuff. Industrial strength components that have been around for decades. The release part is where most of the difference comes into play, right? So we don't need any solvents, which is huge cost saving. We don't have to regenerate every time. Like I said, we're between 20 to 40 cycles, depending on the life cycle of the beads. We don't know what the upper limit is. We're working on figuring that out, but so far 40 is pretty darn good. And then the release process is that low level electrical current. So a square meter box probably takes up as much energy as a toaster oven would. One of the larger units, we think it's going to be somewhere between a high-end laptop and a really nice plasma display, right? So still very, very low amounts of energy that are being used. And that's our biggest differentiator at the end of the day. It's how expensive we end up becoming.
Yeah, it sounds like you could, if you had a literally solar panel attached to the device or available, you could generate sufficient electrical flow to run the device would not even need to be grid attached, which would be a big win for oil companies where, trying to get grid power to an oil field can be extremely challenging.
Yeah, absolutely. And in fact, our first design included solar panels on the top and battery backup on the inside of the unit itself. It still had enough space to hit the levels we wanted to. We could definitely do solar panels. We can't quite fit all of them on the top at this point, but 12 of the high-end solar panels, peppered around the box itself. I mean, and it's, like you said, you don't have to tap into a grid. You can just do it locally if you wanted to.
Yeah. And now talk about the graphene itself. I don't have very little about that particular market. Is there an ample supply of graphite, or where graphene is sourced from? So is that, I presume that's not much of a constraint. I mean, where's carbon and graphite and graphene, I think, are widely abundant.
Yeah, so they are, unfortunately, because we're not trying to build these big, huge sheets of it, right? The graphene chips are widely available, right? It's like not so much dust, but it's like paint flakes, basically, is what it would look like, gray paint flakes. And so there's a significant amount of supply in the market. Our engineering partner gets it from Germany and China. We were talking to somebody else in the U.S. who does a lot of work with graphene as well, and they actually are making their own from biochar. So they're making about 10 tons a year through ultrasound and biochar in Miami, actually. So that's pretty cool. You're seeing a lot of companies start getting interested in biochar and graphene, which there will be no issues with getting enough graphene for what we want to do.
And
not very much.
Yeah, it's thin layer on the outside of these ceramic beads. Yeah. Wow. Yeah. So it's really, really intriguing. Let's talk a little bit about the digital dimension here. How are you applying digital innovations and digital tools to this particular innovation?
Yeah, I'm super glad you asked that. Yeah, because being a pure scientist myself in the past and having worked on some AI projects, one of the first things I glommed onto when we're talking about this is there's got to be a way to bring AI into play. Now, yeah, we could have applied AI models to figuring out the chemistry and all that stuff, but I'm looking more at the operational efficiency of the unit. Right. So, for example, we would have an onboard AGI, which we're developing, that would control the unit itself. You have two benefits there. It's able to manage the unit itself in terms of efficiency, slow the fan up, speed it up, whatever the case may be, more or less regeneration cycles. But it's then also able to do predictive maintenance in terms of this component's about to fail because it's out of these nominal characteristics. Send the tech out to kind of take a look and fix it up, or take a unit offline, for example, right? So I think that's going to be a huge differentiator there as well. That we'll be able to be more efficient than just sitting there running it all the time and switching it on and off every hour. The onboard AI, which will be able to tell when it's appropriate to release and capture.
Yeah, a big plus, but at the same time, I'm sensing that because the technology itself is physical and chemical, the amount of human skill set required to supervise and maintain is actually quite limited here. And so there's another dimension to why this would be really appealing. These gigantic industrial facilities that require armies of engineers and support technicians are obviated here. You don't need that.
Yeah, you really don't. And that was, again, we started this whole process from how can we make money doing this, right? Ourselves. Yeah. And that's kind of what drives every single question. I mean, I guess entrepreneurs at the heart at the end of the day, like, how do we make this financially viable? Because we're not going to depend on capital forever. And that's, again, one of the many reasons why lots of little things added up into what we ended up having here. And that's exactly it. We want these to be standalone. We want clients to be able to just buy the entire unit if they want to, right? Which would be great for us. Take the unit, operate it, 20 to 25 year lifespan. If anything ever happens, things are modular. Just plug something out, slap it back in. All these little spheres are sitting in the canister. We can pull the canister out, put a new one in if we wanted to, like an HP cartridge, shaving razor, right? So yeah, the idea is to minimize human intervention, and within the AI, have it self-optimize. And we also have a cloud AI, which I did talk about. So.
Yeah, well, tell me a little bit about what you see as the kind of the upside here. I mean, there's a lot of atmosphere out there that needs to be cleaned. What is the scale here that makes this particularly growth attractive?
Yeah. So that's a great question, right? So in addition to everyone talking about the US DOE's $100 carbon shot target, right? Yeah. People are also talking about gigaton scale. And no one's even close to gigaton. Not if you're spending $100 million to capture 30,000 tons of CO2. You're not even close to it. Right? There's not enough money in the world to do that. And rightfully so. There are a lot of detractors and a lot of skeptics in the field. But when we come to them, when we talk to them about the size of the unit, the scale of the unit, the cost of the unit, then it's a different conversation. So we believe in eating the elephant one bite at a time. So you take a shipping container at 85% efficiency, it's capturing 1,585 metric tons a year. Well, that may not sound like a lot, but it's a shipping container. Yeah. And it doesn't require specific geology, specific locations. It doesn't have to run off of clean energy because it's so inexpensive. And you can have 10 of these, 100 of these, 1,000 of these, 10,000 of these, 100,000 of these. You can take them to smaller form factors, put them on top of commercial buildings, put them on top of data centers. So all of a sudden the conversation changes. And skeptics become believers. Like, okay, if you can do this at that scale, there's some fire where there's that smoke.
Yeah, there's definitely a market. Is there an angle here that, say, locating the units adjacent to a known quality CO2 source might be another dimension? In other words, rather than say, I'll take a natural gas powered power generating asset, of which there are lots. I know these units are working hard to figure out how to do CO2 capture. Is this at scale? Could this actually be associated with that sort of industrial CO2 source as a part of that infrastructure?
Yeah, so great question. I'm glad you asked that, because one of our first pilots that we're wrapping up and figuring out the timing on right now has to do with exactly that. It's a power generation power generation industry where we're taking the flue gas, they'll filter it and everything else, but they've committed to directly to us. So right off the bat, we're cutting off a small amount of electricity. You don't need to have the fans placed necessarily, right? Yeah. So the air exhaust comes to us, and we're able to capture the CO2 and then pipe it down. They have other plans for the CO2 down their industrial process. Yeah. But yeah, we could integrate. And that's the really cool part is once you start talking to folks in the marketplace, you realize what you've actually created has got legs beyond that. So enhanced oil came up for us. The ability to connect directly into flue gas came up for us. And the fact that these spheres capture specifically a single compound, in this case CO2, really gets us to a point we're going to have those conversations about high purity with CO2 as well.
Yeah.
Without any additional costs.
Yeah. You mentioned at the top of this that you're sort of zeroed in on CO2 because of the volume of it, but I think you also mentioned that you could, with some tweaking of the amine, you could go after different molecules. What other molecules in gaseous form out there could you also apply this to?
Yeah. So while there's other classes of amines that could be used for different gases, we also looked at COFs and MOFs as well, right? So those are different chemical compounds. And it turns out that they can be bound to graphene through this process as well with different levels of efficacy and efficiency, right? The science proves out we use the same science that we did for this, and that worked there, and we have a high level of confidence. This is at this point in time an engineering question. But the idea is we would capture methane, carbon monoxide, and nitrous oxide as well. So we could potentially, we're talking to another potential pilot that has a lot to do with biofuel, and they're looking at methane sources, landfills. Like, hey, could you capture both? I'm like, yeah, you could capture both in one unit. Now all of a sudden the conversation changes again.
Yeah,
right?
Yeah, exactly. Yeah. You can see it. You chain the two devices together, pull the air through one. The CO2 is captured in the first pass. Methane gets picked up on the second, and then you've captured both. Yeah, this could be very interesting as a way to instead of venting or having biogases, for instance. Landfill is a good one. Abattoirs, other one, also produce an a significant amount of methane. You could easily see this being a additive to their industrial process and capture a revenue stream effectively.
Yeah, absolutely, right. And they could decide what they want to do with that, right? So they would pay value-based prices for the units, 25-year lifespan, and they could decide what they want to do with those gases. They could get credits for it. They could sell it as commercial feedstock. I feel like we've really changed the conversation. We're not building huge neighborhood sizes facilities anymore, right? Yep. That have to have clean energy, that have to be on specific geology. Drop these anywhere you want.
Is there, and this gets into the question about zoning and the like, because of the small scale of these things, you really don't have the heavy environmental and zoning challenges that are associated with these large plants?
Yeah, absolutely. I mean, and the biggest differentiator for us is we don't need any solvents, right? It's basically just operates on air and electricity. Yeah. So environmental permitting, I mean, the only thing that I could see potentially being an issue for some regions is the noise level. But you're talking, I think, like 75 decibels at about 10 feet, and it drops off pretty quick after that. And that's with zero baffling, right? We put a bit of baffling, we paint the interior of the unit. We could easily make these much quieter.
Yeah, they can get very, very quiet. 75 decibels, but the sounds of my dishwasher.
It's not very much.
Not a lot of noise. But you can see that. I mean, I know in Australia, noise is a real impact on livestock, and so keeping noise levels down in pastoral settings is really, really important to food production and agricultural settings. So it's good to know that it's relatively quiet. In addition to the fact that it has no solvents, that means you don't have issues related to spills and handling of toxic materials, et cetera. Would be very additive. So tremendous upside, lots of possibilities, and so a great and fascinating story related to carbon capture. There's been an excellent introduction to the topic.
Thank you, Jeffrey. I appreciate you making the time. It's been fun.
Yeah, not at all. It's been another episode of Digital Innovations in Oil and Gas, and please press that like button if it's available, and share this with your network so others can find this content. And I'll return on shortly with another episode. Bye for now.